Let's solve the torsion problem for a rectangular shaft. And we'll do this for the special case where the width of the shaft is significantly larger than its height, which is true for structural sections such as I-beams. So in that case, if we look at the variation of shear stress along the height and the variation of the shear stress along the width, because the section is much wider, the rate of change of shear stress along the width is insignificant compared to the change in shear stress along the height. So therefore, we can take this as 0. And therefore we can neglect this term out of the Laplace equation. So if we integrate this equation twice, we'll get d phi dy is equal to minus 2g theta by y plus a constant of integration. And because the stress function depends on both x and y, so this constant here may depend on x. So if we differentiate again, this term drops out. And then if we integrate again, we get minus 2g theta y squared on 2, which is minus g theta by y squared. And then plus our constant multiplied by y, and plus another constant of integration. Now if we apply our boundary condition, where the stress function is 0 at the boundary, so that'll be at y is equal to plus or minus the height of the section on 2. So what we get is 0 is equal to minus g theta by h on 2 squared, and then plus our constant of integration by h on 2, and plus our other constant of integration. And similarly, if you substituted y equals minus h on 2, we'd get our other equation as follows. Now if we add these equations together, we'd get 0 is minus 2g theta by h on 2 squared, because negative h on 2 squared is h on 2 squared. And then these two terms cancel, and then we get plus 2c2, and then we get our constant is g theta by h on 2 squared. And similarly, if you subtract these equations, these terms will cancel, and the constants will cancel. And you'll end up with C1 is equal to 0. So therefore, our stress function is minus g theta by y squared, and then plus C2, so that'll be minus minus is a plus, and we get h on 2 squared. And now if we substitute our stress function in our torque integral, while taking the shear modulus and the rate of twist outside the integral, because they're constant, then we get the following expression. And here, we're integrating over the width and the height of the section. So you'll recognize the integral of y squared over the area of the section is the moment of inertia about the horizontal axis. So this is well known to be bh cubed on 12. So if we split this integral, we get minus g theta by bh cubed on 12, and then minus minus is a plus, g theta by the double integral of h squared on 4, with respect to x and y. And we'll put in our limits of integration. And note that I forgot to put a 2 here ahead of the integral. So what we can do is just multiply this by 2 to fix that. So this second integral is straightforward to evaluate, which will be bh cubed on 4. And then if we factor out minus 2g theta, we get bh cubed on 12 minus bh cubed on 4. So that gives our torque, which is 1/3 by the shear modulus by the rate of twist by the width of the section by the height cubed. So therefore we can write g theta as 3 by the torque on bh cubed. And now if we substitute this in our stress function can be written as follows. And now if we differentiate our stress function, we get the shear stress on the z face in the horizontal direction, which is d phi dy, which is minus 3 by mz on bh cubed by 2y. And this second term drops out because it's constant. Now if we look at our section, our shear stress varies from a shear stress of 0 in the middle of the section to a maximum shear stress at the top and bottom of the section. So tau max occurs when y is plus or minus h on 2. So tau max is equal to plus or minus the torque by the height over 1/3 bh cubed. So this is the same thing as putting 3 in a numerator. And if we compare this with the torsion formula, where tau max was the torque by the radius of the section on the polar moment of inertia, then we can say that this here is our equivalent polar moment of inertia for our rectangular section.